Okay, guys, welcome back. We are about to start the Dr. Hélio's last lecture. Um, just a minute, please. He's about to share his screen.
I'm sharing the screen. Can you see my screen?
Yes, I can see. We can see your screen. We are ready when you are.
Okay, I'm ready. Okay, I'm going to finish what I started yesterday and see if you can help people have some picture, although very simple, from the neutrinos. So that's where I was yesterday. And I think that's pretty much where we were yesterday. So the idea that I mentioned yesterday that was the concern that Isaac Newton had in 1693, that how things could interact, like the moon and the earth could exchange something. So there was a force between two bodies, like earth and moon, or two objects. But how could that happen without touching each other? So he could not understand. In fact, he could not accept. But the idea, they said, it was a field. There is a field, that there was a way of saying, I don't know what happened. But the idea that we have now is that when two bodies, two pieces of matter or whatever, they interact, like Coulomb's law. Coulomb's law, you have two charge. Basically, you have, say, one charge, let's say an electron. Here we have another electron. And so there is here's the distance that they say r. Okay. Then there will be a force. They will repel each other. Okay. Force here. And this is there's a constant, a key 1, key 2. Okay. There will be a force between them that's just the product of the charge divided by the square of the distance. But how? It's the same for gravity or electromagnetism or whatever. So how they interact. The idea now is that they interact something. They exchange something. So one of the electrons sends a kind of a signal, and the other one captures that signal. So both do the same in the exchange. So the idea is like that. We say that an electron or any particle that has a charge, electric charge, sends a photon. So this one here is sending a photon, and the second electron captures that photon. Or the second electron, this one here, sends a photon, and the first captures the photon. So by exchanging this particle, we see the photon as a particle. They interact, so they know about each other, and something happens. In the case of Coulomb's law, what happens is that they will repel each other. If they were of different charge, like an electron and a proton, so they will attract each other. So, but what they exchange? What they exchange is what makes things different. Okay? If consider just two bodies of matter, like two particles, regarding of the charge, like say an apple and an orange. You have an apple and an orange on top of your table, so they have a mass. And according to the gravity, if you have the same thing, here's a mass 1, and you have a mass 2. And again, there is a distance between them, exactly the same thing as from electromagnetism. Okay, so in that case, there will be a force. Okay, and the force here is the same expression. Okay, the force. Now we call it, the constant is G, M1, M2. Exactly the same expression. But it's of a different nature. What's happening there has nothing to do with the electromagnetism. that happens not because they have electric charge, but because they have mass, like the Earth. So in that case, we say that particles also exchange something that produces the gravitational attraction. This is an idea because we don't know yet. Remember that when you have the nucleus of something like that I mentioned yesterday, like say helium. Helium has a proton and another proton, and it has a neutron and a neutron. And according to Coulomb's law, these the protons will repel each other. They are very close to each other, so it's a very strong force trying to take them apart. But it doesn't happen. It doesn't happen because why? Well, because there must be something here very strong, keeping them together. So we call this a strong interaction. In that case, what they exchange is what we call a gluon. So if they have electric charge, they exchange the photons. By exchanging photons, that's how we have electromagnetic interaction. But protons also have something else that's not electric charge. They have electric charge, but they have something else. And so they exchange what we call a gluon. And for a gluon, it's much, much stronger than what happens with electromagnetic. And so they stay together. But there is another process, like a particle like a neutrino. A neutrino has no electric charge. And the neutrino also does not see this strong force that's keeping protons and neutrons together. In fact, if you have a neutrino very close to an electron, well, it does not feel that electric field, it does not feel the charge of the electron. Right? It's blind to that charge. If you have a neutrino also very close to a nucleus, although there is this very strong thing there holding the nucleus together, the neutrino doesn't see it. The neutrino belongs only to another category of interaction that we call a weak interaction. And the weak interaction also happens because something's exchanged. And in the case of what's exchanged, we call that, in fact, three kinds of particles that are exchanging. It's what we call a W or a Z0. The difference, and they're going to talk a little bit about that, is that the W has electric charge. So when an electron interacting electromagnetically sends a photon, like here, it's still an electron. It doesn't lose anything except some energy because they exchange energy, but it's still an electron. It loses nothing. In the case here from this very strong interaction, whatever they exchange, or the gluon, well, they are still there like a proton or a neutron. They just exchange basically energy together with this gluon. But in the case of the weak interaction that affects the neutrino, things are different. Because one of the things they change is called Z0. Z0 means it has no charge. So when they exchange the Z0, well, they are still where they are because they do not gain or lose any electric charge. However, when they exchange a W, well, the W has electric charge. And one of the principles of having physics is that the electric charge is conserved. So it does not disappear. You can move electric charge from one body to another body, but at the end, it's the same. So, just to have an idea how things work, if you consider this the strong force is the one that holds the nucleus together. So it's very strong because it can even overcome the electromagnetic force. So let's say it's 1 because it's very strong. To compare the electromagnetism that happens when they exchange a photon is about 1,000 times weaker. So the strong is 1,000 times stronger than the electromagnet. And when you go to the weak, the weak can exchange either a W or a Z. Okay? It's even much, much, much weaker. It's 10 to minus 8. So compared to the strong ones, very, very weak. Gravity is here just to be complete, because in fact, we don't know yet. We are suppose that the same happens for gravity, but it's just a theory, it's just an idea. And we don't care about it because, look here, it will be so weak, 10 to minus 37, that doesn't really matter for us. At least that's how I think. But so this weak interaction here, although it's very, very weak, it's very important. Okay? Not just because it acts with neutrino, but because it's basically the interaction that's responsible for radioactivity, the way you see them. And also is very important for the way that particles will decay. Let's see how this pretty much have. Okay. So we have basically four possibilities. A particle, like an electron, yeah, here, it has electric charge, exchange of photons. So this is an electromagnetic interaction. So each and every particle, each one that has electric charge, either an electron or proton, anything, yeah, exchange of photons. That's how it communicates. It sends a photon to, hey, listen, I'm here. Get this photon. If the other particle that's nearby, it also has electric charge, because it needs electric charge to send photons and to receive photons. Then we get some of those photons, and this way they interact. Because when I send a photon, I'm sending some amount of energy, and the other one gets that photon, it also gets some energy. And so that's how they exchange energy. That's how they exchange momentum. That's how a force will show, like in Coulomb's law. Okay? So each and every particle with a charge exchange a photon. But what happens with the nucleus when you have protons and protons, as I said, also have electric charge. So they should exchange photons. But you see, they also are held together, but we call strong force. The strong force is a gluon. So basically what happens is that we have a quark. A quark is a particle that makes a proton, for instance. Okay? And this quark has nothing to do with the electric charge of the quark. Okay? This quark has something, part of the electric charge, that allows them to send gluons. That makes the strong interaction strong. But only quarks can send gluons. Only quarks can. Electrons do not send gluons. Muons do not send gluons. Neutrinos do not send gluons. But all particles that have electric charge. And then we go for the weak interaction. That's the one that we are very interested now. And what is interesting is that all particles, quarks, leptons could be electron, could be a muon, could be a neutrino, all particles take part in this weak interaction. So all particles can exchange and send a W, like here, or they can send a Z. In fact, if a particle like an electron has electric charge. So an electron is at the same time is exchanging photon and exchanging W's or exchanging Z's. Okay? A quark has electric charge. So a quark is always exchanging gluons, or exchanging photons, or exchanging W's, or exchanging Z. A quark can exchange everything. But remember that this strong interaction is much, much stronger. So it will prevail. So it doesn't mean that the other one will not show, but you prevail. The strong interaction will prevail. And here the electron is also exchanging photons and also exchanging W's or exchanging Z. But again, the electromagnetic interaction is much stronger than the weak interaction. Okay, so it will prevail at the end. So most of the time, what we really observe with the electron, most of it is an exchange of photons or electromagnetic. Okay, however, when you go to neutrinos, things change because a neutrino has no electric charge, so a neutrino can never exchange a photon. It does not send photons, does not see photons. It cannot exchange a gluon. It does not even see a gluon or send a photon. But it can send or receive a W or Z. That's how neutrino interact. It's very rare for a neutrino interact, remember that we need a 20 light year long block of lead for a neutrino to interact, because it's this exchanging of W, this exchanging of Z is so weak, so feeble, that's very difficult to happen. So we need a very long piece, a very huge piece of lead, so the neutrino goes to that piece, eventually it succeeds in interacting. So but it can happen exchange at W. But there is something very interesting with W. The W has electric charge. So when a particle, like electron, exchange a W, so electron has electric charge. If sends a W with a minus charge, the electron loses its charge. By losing its charge, it's no longer an electron. So by losing its charge and losing its charge to the W, it becomes a neutrino. So that's basically what happens. The neutrino and the electron are in the same family. We can think this way if we make things easier for us. When we take the electric charge out of the electron, it becomes something without a charge that happens to be a neutrino. When you get a muon, muon has electric charge. If it sends out a W with a negative charge, so it loses charge. Like a neutrino, the muon losing charge becomes a muon neutrino, and the same for the tau. But of course, the other thing may happen. You may have an electron neutrino, right? And when this electron neutrino gets a W, electron neutrino has no charge, zero. But when it gets a W, and he's not blind to that, he can see a W. When he gets a W minus with minus, he gets electric charge. And by getting this electric charge, it becomes an electron, because it's an electron neutrino. If it were a mu neutrino, getting a W minus, it gets electric charge and it becomes a muon, because it's different. No? And the same for the tau neutrino. So what happens? This weak charge is present in all particles. I call it fermions for any reason. So all particles, quarks, electrons, muons, neutrinos, they all have this weak charge in it. Okay? And what happens that when they exchange, happens to exchange a W, their electric charge changes. Okay? An electron loses a charge, it becomes a neutrino. A neutrino gets a charge, it becomes an electron. And the same will happen if you remember here. Where is it? Where is it? Here. Okay? When we talk about the generations, we have the electrons and we have the quarks. Here we have the quark. Quark up, quark down, quark S, quark C, quark T, quark B. And see, they have, although they have their electric charge is not injured, see, the difference between them is 1. Okay? So that's very interesting. That means that if you have, say, quark C here, remember that all particles have this weak interaction. So if this quark C, if this quark C, well, let's say this way here. Let's say a quark C is here. If this quark C sends a W, okay, so it gets rid of 1 unit of charge. So the quark C here has, say, 2/3. But if it loses 1 unity, 2/3 minus 1, the charge here will be minus 1/3. So it goes to where to S, for instance. Okay, so this quark C that has a charge of 2/3 sends a W. I don't like to say lose, but anyway, sends a W. So together with the W has electric charge. Okay, electric charge. Then the C loses a charge of 1 and becomes a particle, another quark whose charge is minus 130. That's not a C, it's an S. And this quark, this W here, something is going to happen with it. So what's very important with this weak interaction is exchanging of W's that allows particles to change. You may go, see, we are going from C to S, but it's also possible the C to go to D. It's more likely to go to S. The T, that's the top quark, may go to S also, by the way. So this exchange of W, thanks to the weak interaction, allows transition from one family to another family. So that's what I'm trying to show here. See, here we have the leptons. Leptons are those that are very light, the electron, the muon, the tau, and the neutrinos. So a W connects them. So from which by exchanging a W, electron neutrino may go to electron, or electron go to a neutrino. The same muon to a muon neutrino. Remember, we said an electron does not go to a muon. What is? No, not material. So an electron does not go to a muon neutrino. An electron does not go to a tau neutrino. They stay all within the family. Okay, but the same may happen connecting the quarks. So you make a W may connect a U and a D quark, a U with an S, a U with a B, a C with a D. So by exchanging a W, losing a W, or receiving a W, you may change this quark from B to U, or U to B. That means it changes completely the particle that's there. And that happens when you have this weak interaction. And when that happens, we see the neutrino always will be present somehow. Let's pretty much see how it can be. Now, this I mentioned already. That happens when you have a particle decay. Yeah? What means a decay? Decay that a particle, we have a particle with some mass. Having some mass means that it has some energy. Okay? And it has another particle, let's say the semi-family, pretty much the same kind, very similar to it, but with a lower energy. Okay, like to give an example, we have a muon, and a muon pretty much like an electron, except the muon has much more energy, it means it has more mass. So what happens is that the muon will decay, will go down to the lower level. The lower level is the electron. The electron stays there because there is nothing below the electron. Okay, so most of the particles will have decay, because most of the particles are, like say, excited states. They look a lot like the ones that are below them, like when you have here. The U, the C, the quark U, quark C, they look a lot like each other, but their mass are different. Some have a much higher mass, as we saw here. Where is it? Let's see here. Okay? See, compare the quark D and the quark S. D and S. Okay? They all have the same electric charge, but the mass is very, very different. So pretty much if the quark S, U, okay, S and C. So that's why they have different families. Okay, so in that case, they may go to each other, they may lose their, whatever makes them a quark C by sending a W. So when that happens, they will decay. It will go to something below. Of course, the opposite may happen. But to go to something up, they must get energy to go up. They must provide energy. Otherwise, they will just go down. There are only very few particles that are really stable. This has nothing to do with being a fundamental particle. A fundamental particle is a particle that has nothing in it. An electron, there is nothing making an electron. Electron is an electron. A proton is not a fundamental particle because a proton is made of quarks. There are 3 particles in there making a proton. So the proton is not a fundamental, but a quark is a fundamental. An electron is fundamental. A muon is a fundamental particle, elemental, because there is nothing making a muon. However, a muon is much heavier than an electron, about 200 times heavier. So a muon may go down to electron that's in the same group. So what they have, the particle decay, something that's below this level, and then decay again, until you get to the lowest possible level, so the final level. In the case of the leptons, for instance, there will be an electron. So a tau will decay to a muon, a muon decay to an electron, and that's it, it stops. And the decay of the particle always happens by a weak charge equivalent. Weak charge equivalent is that process where W is exchanged. So the only one that makes a change in flavor. You may change from a flavor to another flavor, a kind to another kind. Let's see an example here. As I mentioned, the muon is much heavier than the electron. So a muon may decay. So a muon may go to an electron, a muon neutrino, and the anti-electron. See what I have here. You have a muon. The muon has a charge of -1. Okay, -1. Then it sends a W. This is a W minus. So the charge of the muon that was -1 goes away with the W. The W takes that charge. And then the muon loses its charge and becomes a neutrino. But what kind of neutrino? A muon neutrino. Okay. And what happened to this W? Well, this W here goes into an electron and see an antineutrino. Right? But why are antineutrinos? You would say, well, it should be a neutrino, right? No. Remember that I mentioned some time ago that we go after laws of conservation. And as we said, the muon is a lepton. We call it a lepton, name, a word that was invented. And the neutrino is also a lepton. Okay? And the idea we have is that the lepton number is conserved. It means basically that if you start a process with some number of leptons, at the end of the process, you should have the same number of leptons. They will not appear or disappear. The same goes for electric charge. Let's see how this is working here. So the electric charge here is charge is -1. Only the muon has a charge. It was the charge here on this side here. We have the neutrino has 0 charge, 0 from the neutrino. The electron has -1. And the antineutrino electron has also 0. So the charge is also -1. Okay, was preserved. What about the lepton? Okay, lepton. Here we have a muon. The muon is a lepton. So we say that it's L, so much L is equal to 1 lepton. And what happened this side here? Okay, here we have a neutrino, a muon neutrino. That's also a lepton. So L equal to 1. And then we have an electron. Electron is also a lepton, so L equal to 1. So we cannot have here an electron neutrino because an electron neutrino would also be a lepton, and then the lepton number would be 3. So what we have to L equal to minus -1. Why? Because the neutrino anti. So if it's an antineutrino, the lepton number is -1 in the opposite. So at the end, the total lepton number to the right is also -1, is conserved. Okay? Here we have a second example where we have a tau. And the process is the same. The tau has a negative charge. It also sends a W and then loses charge and becomes a tau neutrino. Okay? And this W minus has a negative charge. You have to understand that this particle that is exchanged, the W, the Z, the gloom, or whatever, they do not show. They live just for a short time. They are not free to go around. Okay, so at some time it also comes again, this time with a muon neutrino, with a muon, and then an anti-muon neutrino. And then we ask, is it possible that it goes into an electron, into electron neutrino, antineutrino? Yes, this is also possible. But in this case here, since there has a muon, eventually the muon, the same is going to happen to the muon. So you repeat, and then at the end, you have muons and they have neutrinos. Without the neutrino, this process would not exist. It would not happen. And this is a process that allows things to decay. And that's possible for radiation. I'm going to show next. So since the electron is the lightest charge, the lepton, this is nonsense. Electron is the lightest one, things stop there. There is no process, weak process, whatever, that will preserve energy and momentum. So the electron is stable, it stays there. It does not change. Okay? Now, just a short mention because I'm going to use this right now. Quarks are never free. Okay? The quarks are always together. Either you have a particle with 3 quarks, okay, or you have a particle with 3 antiquarks, or you have a particle with a quark and an antiquark that we call a meson. Okay? This we call a baryon, and this is antibaryon. Why this is important for us? So, electron is fundamental, muon is fundamental. The proton is not a fundamental particle. A proton is made of 3 quarks. A neutron is not a fundamental particle. A neutron is made of 3 quarks. Not the same quark arrangement as a proton. That's what makes the difference. And each particle has its antiparticle. So the antiparticle for the proton that looks pretty much like a proton, but it has a negative charge, will also be made of quarks, but in that case, antiquarks. So remember here, yeah? At the very beginning, I showed this thing here. What the explanation of Pauli gave to this process where they have tritium going into helium, and then he proposed, well, there is a, now we call it neutrino here. Remember what you have in the tritium? Tritium was this yellow here, it would be a proton. Now, let me use the same color just to make sure things are clear. Say, like your proton. Oh. Ah! Is a proton. And here's a neutron. Thus, this is a hydrogen with 2 neutrons, a tritium. And now what we have here is one neutron, and then proton. See, we still have 3 particles in there. Okay? But here was 1 proton, 2 neutrons. Now we have 1 neutron and 2 protons. That's basically what's going to make the helium atom. Well, that sounds interesting. So basically what we see there is the following. Hey, listen, one of those neutrons turned into a proton. Wow, how is that possible? Remember that when a particle exchanges W, it loses or gets electric charge because the W has electric charge. And the proton is a neutral particle, has no charge. But if it loses electric charge like a W, if a W takes away a negative charge, the result is that it gets positive. And then a neutron getting a positive charge becomes a proton. Okay? They did not know that on those days. Okay? They have no idea of the neutrons, the protons, and how the things work. They did not know about that. But now that's what we know that happens. So let's see here how things work. See, the proton, the mass of a proton is about 938.3 MeV. And the mass of a neutron, so it's almost the same, but it's bigger. So the mass of the neutron is bigger than the mass of the proton. Basically, it means it has more energy in a neutron than in a proton. A little bit more, not much. And when it comes to quarks, what they have, the neutron is 3 quarks, as I mentioned, is a quark U and 2 quarks D. That's what they have here, quark U and 2 quarks D. If you go back there, where is it? Quark U and D, right there. Where is it? See, the quark U has a charge of 2/3, and the quark D minus 1/3. Okay? So the D has minus 1/3. The other one is minus 1/3. And the U has 2/3. 2/3 minus 1/3 minus 1/3 is 0. Total charge equal to 0. So this is a neutral. Okay? But then what they have, at some point, one of the D quarks, see here, loses a W, emits a W. By emitting a W, it loses energy, loses electric charge, and then becomes a U. Okay? Now, U is no longer a neutron, but it's a proton. And what happens to this D here? Well, the D here goes to an electron and to an antineutrino. In fact, what they observe in the thing that Pauli proposed, what's coming here is not a neutrino. Okay? What is coming here is an antineutrino. An electron antineutrino comes. This is the process of what you see. From outside, we see an electron and the antineutrino coming. So the process, this one here, have the D. Okay? The D exchanges the W. So his charge changed and becomes a U. So since it was within the particle making a neutron, now it will be a proton. And from this W minus, the electric charge is preserved. Okay, then will be. So I have a minus here. The minus we show here in the electron, and then we have the antineutrino here. So without the neutrinos, these things would not happen. It would be very, very different. Okay, so that's what has happened then. And then that's what happened in the radioactive process. Okay, so neutrinos are again there, taking part of this process. It's an antineutrino, but okay, it doesn't matter for all practical purposes here. We still do not know if neutrinos and antineutrinos are really the same. So this thing is very, very confusing indeed. So just to go a little bit brief, how neutrino is going to happen? So what you see, the only way that neutrino interacts with something, means that it perceives something, it does something, is by exchanging a W, or maybe exchanging a Z. If it exchanges a Z, the Z has no electric charge. So if a neutrino exchanging a Z with an electron, well, the electron is still an electron because it does not lose or get anything, and the neutrino is still a neutrino. What changes is that there will be a transfer of energy from the electron to the neutrino, or vice versa. They just exchange energy, or maybe exchange momentum, but the charge are the same. So a neutrino at the very end is still a neutrino, and the electron is still an electron. But if they happen to exchange a W, then you may have a situation when you have a neutrino and you have an electron. I say here you have a neutrino, you have an electron, and they exchange a W. So what may happen? They exchange a W, then the electron loses its charge and becomes a neutrino. And the neutrino becomes an electron. Fantastic, no? So although at the very end, you still see an electron and a neutrino, and they are really not the same as the beginning, because they exchange a W. So the electric charge went from the electron to the neutrino, from the neutrino to the electron, doesn't matter, right? If you take electric charge, if you take 1 unit of electric charge from a neutrino, it loses 1 unit of electric charge then becomes negative. If the electron has a negative energy, a negative electric charge, if it gets 1 unit of electric charge, it becomes 0, and then it's now a neutrino. So at some point, a neutrino, the only way we interact with something is exchanging a double, or if they exchange, if we have here, and here have an electron. If they exchange here a Z, what happens? That's we still have a neutrino, and they still have an electron. They not change. What's changed? Well, the electron will give energy to the neutrino, or the neutrino will give energy to the electron. At the end, one will have more energy than the other, or they will change direction, right? But they will still be an electron and be a neutrino. But for that happens, the energy involved is important. Okay, nothing can happen with less energy. If you have a process of any kind, okay, that requires a certain amount of energy to happen, and you don't have that energy at the beginning of the process, it is not going to happen. So here we have a neutrino. Have several examples of neutrino, and depending on if it does not have much energy, the neutrino will say interact only with the whole thing. But to start going into the atom, and then get into the nucleus of the atom, and then getting into the nucleus, getting into the proton, and then getting into the proton, go there straight with a quark as the proton, is require more and more and more and more energy. As more energy, more able to do. Because if it does not have enough, let's say that the process will be in such a way, as I said here, that the neutrino here exchanging, say, a Z with an electron, and the consequence is that the electron will change direction, move to another direction. It takes some energy for that, okay? And the neutrino cannot send more energy to us. The Z will take energy, the W will take energy, but cannot take more energy than is available. So if the process requires more energy to happen, maybe you need neutrinos with more and more energy. Otherwise, you don't have enough energy for things to happen. That's what I'm trying to show here. If you want more, you need more energy to go deeper, deeper, and deeper, and deeper inside. And that's what we do in experiments. And the reason why we try to build accelerators with more and more energy, because for a neutrino or proton, whatever, to transfer energy, cannot transfer more energy than it has. Okay? And it's not going to transfer everything because it will just disappear. Okay? It cannot transfer everything. Here, when they exchange a Z, the neutrino is still a neutrino, so we have some energy at the end. So it cannot transfer everything, cannot transfer all its energy, and cannot certainly transfer more than it. So if a process requires, say, 1 GeV of energy to happen, and if you have a neutrinos that they have an energy of half GeV, that thing is not going to happen. No way. So, and if you have neutrinos with 1 GeV, and that's the energy you need, well, this is not going to happen. So you need more and more and more and more energy for things to happen. Now, let's talk about some strange properties of the neutrino. And these strange properties connect with helicity and chirality. Okay, what's helicity? Okay, the idea is very simple. Helicity is the projection of the spin along the particle. The spin for all practical purpose is not like that. Let's think a particle spinning. Particle is spinning here, spinning. Okay, it's spinning, and at the same time it's spinning, it's moving in a direction, moving here, and the spinning here. Okay, and so we project the spinning in the direction of movement. So, in principle, you could have the following: you could have the particle going this direction and spinning like that, or you could have the particle going that direction and spinning the other way around. Okay, that's the two possibilities. Okay, it may be spinning like a corkscrew. Or a screw. It can go forward, spinning right hand, or go forward, spinning left hand. Okay, the one here is right. hand, and this one is left hand. Why right hand? Okay, if you get your thumb, if you have your thumb here, the other, you have your thumb pointing the direction of movement, and then the other fingers going around. See, the one to the bottom is your right hand. Well, the fingers are pointing, the right thumb is pointing direction, and then the other four fingers go around as the particle is spinning. The one at the top is the other way around. The other one at the top, you have to use your left hand, get your left hand, your thumb in the direction of movement, and the other fingers will go around the movement. So those are the only two possibilities. If the particle is spinning, moving, either is spinning as your right hand or spinning like your left hand. Okay. Most screws that you have, right hand, use the right, turn it right hand, the right direction to put the screw, and left hand to remove the screw. So there are the two possibilities, and then you call this the helicity. You may have right hand helicity or left hand helicity. Okay, the only two possibilities we have. The problem of 4 p.m. The problem is that depends on the frame of reference. Let's see that you have here, this is a ball, I am exaggerating, okay? The frame of reference in the car. Let's say that the car is going slower than the ball. Okay? So it means that the ball goes faster, okay? And the balls are spinning here, as I see, okay? So what people in the car will see? People in the car will see the ball with a right hand helicity, the same ball. However, if the car and the ball are moving at the same speed, okay, so from the car perspective, the ball is not moving at all. So we cannot talk about helicity because the spinning of the ball is not in the direction of movement of the ball because the ball is not going anywhere, according to the car. For the car, the ball is not moving, it's still. So the same situation here, the same situation, but since the car is going slower, the car sees the ball as right hand. The helicity is right hand. Here, the car does not see any helicity. The ball is not moving. And if the car goes faster, if the car is going faster, like the car see the balls going backward, going that way. In that case, if it's going back way, see, use your hand. In that situation, you have your left hand here, pointing in the direction of the ball, and there are the fingers of the left hand that goes around the movement. So in that case, you have a left hand helicity. See, the first one is a right hand helicity. The ball is going ahead. The spin did not change, in fact, but now it's the right hand. Here is nothing, and here is left hand. So helicity is a property that depends on the frame of reference, where you are. We don't like this, okay, because we're going to fight. I say this is right hand, say now it's left hand, both are right. So it's not something that is intrinsic to the system. This is not a property of the ball itself, okay? Now, is there something that is a property? Well, helicity depends on the frame of reference. So it's not an intrinsic property of a particle. Say, a particle, an electron has a negative electric charge. It doesn't matter where you are. It doesn't matter your frame of reference. The electric charge of electron is negative, okay? But if you start talking about helicity, well, no, it's not a property of the electron. Depending on the situation, the helicity may be left hand, right hand, or no helicity at all. So, but is there something that could be a little bit related to helicity that's invariant? It doesn't change with position? If the symmetry means something, that doesn't really matter, this thing. We're just wasting time. So then we have to talk about chirality, a chiral, chirality. Something chiral if it cannot be superimposed to its mirror image. Very strange, right? Let's see here. I have two situations here. Here I have a screw, and here I have a nail. Okay, and here's a mirror. Now pay attention here. If you see the image, the reflection of the screw on the mirror is not like the screw itself. See, here we have the thread this way. But the one you see in the mirror is this way. So if I try to get this screw and superimpose it on top of the mirror, they will not coincide, right? They will not coincide, not be the same. So a right-hand screw shows on the mirror like a left-hand screw. But this doesn't happen with the nail. The nail is the same. So in fact, if nobody tells me anything, I cannot know if I'm looking at the mirror or the nail itself. On the other side, if I know that the screw is right hand, okay, and I see in the mirror left hand, I say, this is not the screw. This is the mirror image of the screw. So this sounds very strange, but then we say that this screw is chiral, and the nail is a chiral. So a particle that cannot be superimposed, basically that the image on a mirror is different, right? Is chiral. The other one is achiral, has no chirality. And so what? Is this a big thing? We're just wasting time. Would nature cares about that? Well, it does. That's very interesting. It does. It's all around us. If you take DNA molecules or whatever, look like a spiral. You see there, right? Helix. And you have here what you call a DNA, a B DNA, a Z DNA. And you see here it's a spiral. See? And this one here is right-handed. And that's always like that. Nature does not make two kinds of DNA. They are all, in this case here, right-hand. So nature decided, well, no, I don't want a left-hand DNA molecule. No, I don't know why. Well, I don't know why, but that's how it is. The way the molecules get together is such a way that DNA is not to be left-hand. So if you show me a DNA molecule structure that's left-hand, look like a screw going the other way around, I would say, no. This is a mirror image. This is not one. Why? Well, because nature only does right hand once. Okay? It's strange, well, but that's so nature like this. And chirality is also around us. For instance, here's a molecule. I don't know the name of this molecule, but okay, this is a molecule here. And here's a mirror. Okay? And here how the molecule look in the mirror. So it's inverted. So everything was inverted. Okay? And you may say, okay, it's the same thing. It doesn't matter. But Mother Nature comes and says, no, it's not the same thing. I don't like this. I only make this one. I don't make this one. I don't allow this one to happen. Or the other way around, whatever. So although you may think that's the same thing, it's just a question of putting things the other way around. Nature does not think this way. Nature does not think this way. This may be strange, but that's how it is. So chirality is present. Nature prefers sometimes left hand, sometimes right hand. Oh, sometimes doesn't matter. Let's say Donald Trump, for instance. He's Donald Trump. It's a picture of Donald Trump. Okay? See, it's not chiral. It's not symmetrical. If you take this picture in a mirror, you cannot superimpose them. The hair is totally out of proportion. So if you take the image in the way all the way around, they will not coincide. So Donald Trump is not chiral. It's a chiral. And more than that, Donald Trump interacts only with the right. He ignores the left completely. So Donald Trump interaction is also chiral. His interaction also prefer left over right. So not just he himself is chiral, but the interaction that's associated with him is also chiral. He could interact in both ways. Okay? And so what? This is just a joke? No, it's not a joke. It's not a joke. And basically, what I did with a bolt, a screw, and a nail, I want to do now with a particle. Okay, let's get a particle in front of a mirror and see if the way that particle shows in a mirror is the same as the particle. So let's get an electron, put the electron in front of a mirror and see. Can I do that? Well, no, I cannot do that. Of course, I cannot do that. I cannot do that with an electron. I cannot do that with a neutrino. But how do I do that? I can do that in a mathematical point of view. Okay? Let's see what happens here. Here I have a system where you have the x, y, and z axis. Okay, and let's make an operation that they call parity operation. What I do is very simple and it looks trivial. I just change x, I invert x, I invert y, and I invert z. Okay, that's what I did here. See, x was inverted, y was inverted, and z was inverted. So by inverting three of them, basically replacing x, né? X minus x, y minus y, and z minus z. That's what I did here. Okay, I have another system. Now, look the system here to the. In the system here, if I apply the same system and I move, rotate x, y, okay, the result. Remember this operation that you do with vector analysis or whatever. So if you rotate x toward y, we get in this direction here. See? So this is a right-hand system. A right-hand system. Here, well, here, if I rotate the x to y, it comes this way here. Look, this way here, rotating x toward y, I get in the direction of z. If I have vector analysis, usually I call this the unitary y, j, and k, right? So what I have is I vector j is equal to k. But here, see, if I do this from here to this one, I don't have j, will be, in this case here, x, I vector j, okay. But here, if I have x prime, gosh. If I have y prime, vector j prime, the result is minus j prime. It's the other way around. So the system to the right is not a right-hand system, it's a left-hand system. So by just changing x by minus x, y to minus y, z to minus z, I go from a right-hand system to a left-hand system. And that's what I can do to see a left-hand or a right-hand electron or neutrino. So I represent, in quantum physics, we represent a particle. Would be an electron, would be a neutrino, we represent by a wave. Maybe, probably you saw that already. And a wave, there's a function of x, y, z, and t. Okay, so we have a wave representing an electron. So if I replace that wave, the x, y, and z for minus x, minus y, and minus z, I am changing from right hand to left hand, like getting the electron in front of a mirror. You see what happens there. So I may have a right-handed electron, and then in the mirror I see a left-handed electron. Okay, or I have a left-handed electron, in the mirror be a right-handed electron. And then I do the same with a neutrino, of course. I get the neutrino, that will also be another wave, that will be x, y, z, and t. And then I have this wave, and I have that on the mirror. Then, if I have a right-hand neutrino, and I change x, y, z, I see in the mirror, and then the mirror will be a left-hand neutrino. If I have a left-hand neutrino, in the mirror will be a right-hand neutrino. So I can have both of them. I can see how it would be a right-hand or left-hand neutrino, as I do with an electron. Here it is. The problem is, and this is surprising to some point, as neutrinos are chiral, what happens is simply we do not see right-handed neutrinos. Period. We don't see it. They don't exist. Electrons, okay. Electrons, you may have electrons that are right-handed, and you may have electrons that are left-handed. Okay. They have, in fact, they have both the components. Part is right-hand, part is left-hand. But neutrinos are not. At least we never saw them. For our surprise, we always see only left-hand neutrino. So a left-hand neutrino is picture of the neutrino in a mirror would be a right-handed neutrino. And this picture in the mirror does not exist. The same way as we do with that DNA molecule. The DNA molecule is a right-handed molecule. In the mirror would be a left-handed molecule. And this thing that we see in the mirror does not exist. So by making this operation, this parity operation, change, like putting in the mirror, you see something, you produce something that does not exist in nature. See, this is not the case for an electron, okay? If you have an electron, left-handed electron, the electron in the mirror that you see here, a right-hand electron, can I know if it's a real electron or not a real electron? No, because both are possible. We can have a left hand and a right hand. So I don't know. But if you show me a right-hand neutrino, say, no. There is no such thing as a right-hand neutrino. I don't see. So what you see in the mirror is not real, does not exist in nature. We only see left-hand neutrino. And so, not surprisingly, the antineutrino is the opposite. Antineutrinos are always right-handed. So if you see someone shows you a right-hand, so a left-hand antineutrino, you say, no, that's not possible. This doesn't exist. You are just getting the picture in a mirror, and you see in a mirror does not exist. So you can distinguish the mirror from the real thing. And so, to make things worse, the weak interaction also distinct, like Trump. We only have left-handed, but the weak interaction is not like Trump. It's the other way around. The weak interaction couples only to left-handed particles. So the neutrino is left-hand, it's a left-hand particle. Okay, so interacts with the weak interaction. W makes this. And the electron, well, okay. But if you get a particle that's right-hand, if you have an electron that's right-hand electron, it does exist, no problem. But this right-hand electron will not interact to the weak interaction. So this is very strange, in fact. The weak interaction favors the left hand, and neutrinos only have left-hand neutrinos, so it's okay. It means that violating parity means the following. When I get that picture of the mirror, in principle, I should have also physics should still be there. It happens when I work with an electron. So I change it from right to left hand. Well, okay, it's still there, different. But this does not happen with the weak interaction, does not happen with the neutrino. But the one thing that we should think about is that it really happens because, see, the neutrino only interacts through the weak interaction, exchanging W, this thing. And you only see left-handed neutrinos, right? But the weak interactions also only goes to left-handed particles. So if there is a right-handed neutrino, we don't see them. How do I see them? It means that it does not interact because it has no electric charge, so we cannot exchange a photon. Okay, so that's it. Well, cannot interact exchange a gluon because we can exchange only to the weak interaction. But the weak interaction does not care for right-handed particle. So if there is a right-hand neutrino, it doesn't interact. That we could call a stereo neutrino, a neutrino that does not interact. If it does not interact, it may be hard to see because it's a little bit strange to think that there is no right-handed neutrino. Also, if you advance a little bit longer and you start to see how particles get a mass, the process that gives particles a mass, like an electron or a quark or whatever, we see that process should result in particles with right-handed particles and left-handed particles. So an electron has left-hand, both has left-hand component and has a right-hand component, both of them. The process for producing mass, the way you think nowadays, produce both. But nowadays, we know that neutrinos have mass. Remember the oscillation that I mentioned? Neutrinos have mass. But then the process that we understand, or at least we think we understand, that to give particles a mass should produce right-hand neutrinos also, but it doesn't. So the process is wrong. Our theory is wrong. Neutrinos do not fit into this theory. Something must change. Okay? So, or maybe there is this neutrino. We really have neutrinos with right-hand neutrino, but you cannot see because the weak interaction does not interact with the right hand, which also does not fit well in theory we have. And see, the right-hand neutrino, if it does not interact with anything, could be very heavy. It does not. The reason why neutrinos do not interact a lot is not because they are very light. It has nothing to do with their mass. The mass would affect only gravity. And we do not care about gravity. So, in principle, we may have a neutrino that will be a particle with nothing, with no charge, no electricity, no exchange, no photon, no gluon, no W, no Z, whatever. It could be very heavy, very massive, but we cannot see. So it does not see, is it a possibility for us to detect such particles? Oh, yes, to some extension, yes, there is some possibilities. And let me talk to you about some story that probably you heard about. There is a story that goes to time of the Greeks, and the king had gold and had to have a crown made from gold, and he was concerned about, well, the guy doing the crown could get some of the gold for himself and replace it by, say, copper or any other metal. Okay, how could the king know if the guy was stealing some of the gold? Okay, let's say you have here 500 grams of gold, okay, to make it a crown. And the guy who's very smart, he takes 100 grams of gold for himself and adds, say, 100 grams of copper. So at the end, the queen gets a crown that has only 400 grams of gold and 100 grams of copper. It's the same amount, 500 grams. He cannot really see the difference. Well, so he loses. But then a guy, Archimedes, came with a great idea. He found out, okay, we cannot see this copper in there, but he found out the thing that now we call density. So 500 grams of gold has a density, so occupy a certain volume. But if you have 4 grams of gold and only 100 grams of copper, the density will be different, the volume will be different. So by comparing the volume to the weight, he could see, oh, listen, some gold is missing here, although he could not see it. Something similar could happen with neutrinos. Remember that we talk about oscillation of neutrinos, right? And you get an expression that will give you the probability of oscillation. That probability of oscillation at some point showed something that was the mass difference. Say E. Okay? Okay. And we did that so that basically for 2 kinds of neutrinos, could be electron and muon neutrino. But now we know there are 3 neutrinos, electron, muon, and tau neutrinos. So that expression will be a little bit different, but that expression we show this square, the difference square of the masses of 3 of them. Okay? And then we can calculate that, and then we can measure the probability, the oscillation probability, and then compare the oscillation probability, all that expression, with the calculated value. Now, this 4th neutrino, if it do exist this 4th neutrino, this will be another kind of neutrino, it will affect this oscillation. If it does not show, cannot interact, the probability of oscillation will be different, because imagine it has a very big mass. If it has a very big mass, the difference could be big and be noticeable. So if you measure the probability, the oscillation probability, very precise, very high precision, and then compare with, okay, what is the result if you have 3 neutrinos with the masses that we know? And what happens if we have 4 neutrinos? So we can know if there is something missing, and maybe we can detect the presence of this 4th neutrino But for that, we need a very precise measurement. And that's what the new experiments try to do. An experiment like Doom try to do that. We're going to measure oscillation parameters with very high precision. And by doing that, you can see if the oscillation of neutrinos and the oscillation of antineutrinos are the same, if they happen at the same values. If they do not happen the same value, it shows that there is a difference, an asymmetry between neutrinos and the antineutrino. And this could explain the difference between matter and the antimatter. So to finish this very short presentation that at some point I understand is very confusing because lots of things about, we can say that neutrinos basically do not fit into the theory that we have now. There is a theory that goes very well, very nice, but neutrinos don't fit there, period. Okay? I have to change something. The theory must be changed. We get a new theory, add something. Neutrinos have always been a source of surprise. Everything you deal with neutrinos, things do not go the way we expect. Has been since the beginning and until now. Because they think that there is no right-hand neutrino, and maybe there is this heavy neutrino, and this difference in mass. We don't understand how neutrinos have a mass if the system we understand the mechanism that produces mass does not work for the neutrino. Okay, so neutrinos point to what we call a new physics. The physics that we do not understand, you have to understand. And neutrinos may be behind this matter-antimatter asymmetry, but for that we have to really understand well how neutrinos operate, how they exist, what are their properties. They oscillate. This oscillation is the source of all this mass that you notice. And they are so basically still a sort of a mystery. There are lots of things that we cannot answer, and it has been very hard to study neutrinos exactly because they are hard to interact. It's hard. So nowadays, with very powerful neutrino beams and very big detectors, we are advancing and getting more and more. But as more we advance, more surprises we have. We get things that we do not understand, not fit our model. So what's the origin of the mass of the neutrino? Neutrinos, by the theory we have, they should have no mass, but they have a mass because they oscillate or they oscillate. Or maybe all this is wrong and it's different. We should go around to another theory. And are there right-handed neutrinos? Yeah, maybe. Why not? It's strange that there is no right-handed neutrino. Are there heavy neutrinos? Maybe. We have to study. So stay tuned. There are surprises still to come in the horizon. And many groups, including groups from UNI with Professor Castromont, have been working in neutrino experiments. And it's very exciting field to do, very exciting, because we are working really at the boundary of physics, of what we know today. So we are very close to making big discoveries in physics, to understand better the universe. So for
Or not.
you, for what?
Or not. Or none of them.
But then there will be questions without answer. We are not happy with that, right? We have to understand what's going on. Maybe someone come with a theory. So that's an interesting point. Even if you run all these experiments, if you don't get the answer, this is still an answer. Say, hey, listen, things don't work. It's not like that. So it's exciting field to work. And for people who are starting now, things are going to happen or not happen in the next few years. And the experiment like Dune will start collecting data in 2026. That's only 5 years from now, let's say like that. And then maybe we'll be able to find some of the answers. Okay, that's all what I had to do. I know that these 3 days is not enough for us to cover. I try to show it. I try to present things in a way that we have more questions than answers. And if this was enough to bring your attention to neutrino, that's good. We have achieved something. So I thank you for the opportunity. And well, anyway, any question?
Is there any question? ¿Preguntas, muchachos? ¿Alguna pregunta, duda, comentario?
Criticism. You can also criticize.
Ah,
You
críticas.
can only say all this. You can also say this is all nonsense.
Yep.
If you want. If you don't understand things, you are not alone. Okay, don't Don't say, oh, I don't understand anything. This is so messed up, so confusing, because this is confusing. Even big guys are confused.
Is there a left-handed Trump?
It's okay?
Is there a left-handed Trump? It's my question, Carlos.
Yeah, hello.
That's
My question
yes, we
is,
have to look around. Maybe.
Go
I don't know
ahead.
if you can hear me. Well,
Yes,
my
yes, we
question
can.
is, what is the most promising experiment in neutrino physics?
Of course, our experiment is the most
Obviously.
prominent. Obviously. Now, okay. In fact, there are several neutrino experiments. Okay, the big one that's being under construction now is Dune, that I mentioned. But there is another big one. That's a hyper K. It's hyper K. The name, I even forgot. Hyper K, right? That's also projected. I'm really not sure about how this hyper K experiment is going on, but I know about Dune. Dune is a huge experiment, has thousands of people around the world. Is the experiment that has been designed to try to answer some of those questions. Okay, because the point is the following. Let's say there is a difference between neutrino and the antineutrino. The probability. This difference does not have to be a huge difference. If you are a huge difference, we have already seen it. Okay. If you want, say, if you have something that is 100 kilograms heavy, it's easy for you to see the difference in mass from an elephant to a dog. Okay. But if you have an elephant and the elephant has a flea on top of it, it's very hard. Okay, to see. It's the difference between 2 tons and 2 tons plus 1 gram. So if there is a small difference, this difference between neutrino and antineutrino that would explain the mass difference in the world does not have to be a fantastic difference. A small difference would be enough. Okay? But exactly because the difference may be small, and if there is a difference, it's small, means that the measurement must be very precise. Huh? Like in the case I mentioned, an elephant with a flea. An elephant has 2,000 kilograms. The elephant with a flea has 2,000 kilograms plus 1 gram. Most of the scales in the world, you not see a difference. You not be so you have to be very precise. Hey, listen, this one has 2,000 kilograms, and this one has 2,000 kilograms plus 1 gram. So the measurement for neutrinos and antineutrinos have to be very, very precise. And you need also very high statistics. You cannot do that only with a few neutrinos or a few antineutrinos. So you need a very, very intense beam, because a very, very intense beam means that you have millions and millions and millions of interactions of neutrinos, because then you have very high statistics. If you have only 10, only the statistical fluctuation will destroy the measure. So you need a very big beam. Do have a very intense beam, and they also very high precision. Very high precision, your detector must be able to distinguish very well the process. You must understand all what you call the background. So Dune is a promise that Dune will be able to see a difference between neutrino and the other. There are hints already, okay? People are not just guessing. There are hints that this difference between neutrino and antineutrino does exist. There are some hints that there is about the value or so. So the experiment is aimed to see this difference if it really exists. So it's not a guess. You don't make something that costs hundreds of millions of dollars just out of a guess. You have to say, okay, listen, I have a hint. There's a real possibility that this is going to happen. And so Dune is the experiment to go. And people at Uni are involved at Dune.
Oh, what's happened?
Is there any other question?
Hélio left.
Pues, está tímido. Esperemos para regresar, pues.
Yo tengo otra pregunta, profe. Por ejemplo, hay fuentes de neutrinos, o sea, ¿se puede identificar una fuente de neutrino o más o menos saber de dónde viene, de qué parte del cielo se observa? Pero
Sí,
¿cómo identificas esencialmente, por ejemplo, cuál es la fuente? Porque, por ejemplo, puede ser un centro de una galaxia o puede ser una o otra cosa que está detrás. ¿Cómo identificamos la fuente exacta?
son múltiples observaciones, o sea, tiene que haber...
Am
general
I back? Am I back?
Yeah, you're back.
Ah, sorry, the connection dropped. Okay, go ahead.
Se volvió
You
ahí.
just left.
Se cayó otra vez.
Déjame ver. And you just left. Ajaja.
Okay, I'm back again. Sorry. Go
Okay.
ahead.
There is one more question from France. He's asking about how do you determine the direction of I say the origin of, for instance, for an extragalactic neutrino.
Ah, it's easy. Let me try to go. Am I still sharing my screen? I don't know.
Yeah, go ahead.
Okay, Nisha. Okay, let me see. Let me use this sketchbook. Okay. Okay. Okay, let me say I have the color. Let me get black. Okay, let's say I have here my detector. Okay, my detector. In fact, let me do it a little bit bigger. And detector. It's not a square. And here we have the lab, like say Fermilab. Remember, Fermilab sends a beam of neutrino. A beam of neutrino, and that's travel about say 1,300 kilometers. Okay, and here's my detector. So, and one of the neutrinos gets here and interacts here, producing something. Okay, when it produces something, it will be a result. If you remember that film, that video showed yesterday. So, and we make what is say a reconstruction. The reconstruction from the signal that we get from the four multipliers, we try to redo what happened. Then there are two things that are very important. First, there is a clock. Okay, so we know when Fermilab is sent. We know when Fermilab sends neutrinos. We know when it's sent, and we know the distance. So this is all synchronized. So we know exactly when neutrinos are arriving here in the detector. So everything that happens in the detector that does not coincide in time with the beam, this is not coming from the neutrinos from Fermilab. Okay? First thing. So anything that happens out of this time window is not coming from Fermilab. A second thing is that since we reconstruct this, we know the direction. By reconstructing this, remember we have conservation of momentum, and so you know that this is coming from there. Something that happens here in a supernova, for instance. Yeah, it's when I've sent neutrinos para cá, in this way. First of all, of course, the supernova is not going to be synchronized with the lab. So neutrinos from the supernova will come totally out of synchronism with the lab. And second, a neutrino from the supernova will be a very intense burst. We produce something here that will come, say, this way. So by reconstructing this thing that happens here, we see that it's coming from there. It's not coming from the lab. So you know exactly the direction from where it's coming. So basically things, time, we know if the event is coincide with the time that the lab is sending the beam, the neutrino, and the direction. We reconstruct the direction, you know it's coming from up there from the space, from a supernova, from where. So this is not really hard to know because of the direction and time, let alone the energy also, right? When you reconstruct the event here, all the reconstruction, remember, energy is something that is conserved, preserved. So the energy of the neutrino, when you reconstruct the event to see what happened, you know the energy of the neutrinos, right? The lab is sending neutrinos, we know the energy of the neutrino. So we know the energy here. So from a supernova, the energy would be very different, much higher than the energy from the neutrino. So the energy will be different, the direction where the things come are different, and the time is different. So there is no way we can mix. Unless, of course, there is a supernova that happens to be aligned with the detector. Here is the detector, here is Fermilab, right? And it happens that the supernova happens to be exactly aligned with Fermilab, and it happens to burst exactly at the same time of Fermilab. But even so, the energy will be very different. And also, the Fermilab does not send neutrinos continually. In fact, send pulses. So, neutrino. So the neutrinos are not, neutrino beam is not continuous. So everything is very different. It's easy to distinguish. Okay?
So, but what happens if we have, I don't know, two supernovas in the same direction?
Then,
How we can identify the
if you have
origin?
having two supernovas in the same direction, gosh, it's very hard to have one supernova. It doesn't happen. We don't know about supernova, but you know they are rare. Having two supernovas and the same direction have at the same time, well, I
Quite
think it is
improbable.
it's extremely unlikable. It's easy
Unlikable. Yeah.
it's easier to get in the lottery, much easier.
Or maybe one supernova and then one origin or of some galaxy. I don't know.
Again, at the same time, in the same direction. And understand, if this happens, probably we're gonna miss it. It's very likely they not even consider that, because remember, it's not. Let's say you have two supernovae in the same direction. Okay, let's consider that you are a very lucky guy. Okay, you are a very lucky guy. Let's see the following. You have here one supernova, supernova 1, and here you have supernova 2. Here you have the detector. Okay, let's say the supernova 1 is, say, 5,000 light year. The distance. And this other one is, say, 15,000 light year. Okay, so if I see a supernova that's 5,000 light years away, it means that the supernova really bursted 5,000 years ago, right? Because, and so this other one is 15,000 years ago. If the signal gets here at the very same time, that's extremely coincidence. It means that the other one bursted, exploded 15,000 years ago in exactly the same synchronism with the supernova 1. This is not going to happen. This is simply not going to happen. And if that happens, we're going to think that's only one supernova. This is extremely unlikely. It's not going to happen. Supernovas do not happen every day or every year. They're very rare. I do not even remember when it was the last one.
1987.
1987. 97.
Yeah.
How many years ago? It's 97.
A lot.
2000. 30 something years ago. It's
Yeah, there's
very,
something.
very, very, very rare. This is not going to happen. Buy a lottery ticket. Chances are better.
Yeah.
More? Anything else?
There is
So
another question.
if you have more questions, you can always write it to Professor.
Yeah, there is another one, Hélio.
Okay.
And
Which
there
one?
is another guy just coming in. How do you determine when measuring neutrino from the sun, what neutrinos come from the sun or from some other sources?
Again, the same answer. We know where the sun is, right? We know the sun is there. Yeah? So when you get neutrinos, first of all, the sun is very close to us. Right? The other star, the closest star is Alpha Centauri, that's about 4 light years away. So the sun is a very intense source of neutrinos compared to any other star. So there is no way to confuse. And again, we know where the sun is. We see the sun every day. It's not even difficult. So we can know exactly from where the direction of the neutrino that's coming, where it's coming from the sun. This is easy. We see the sun, not a problem. And again, they had the question of the intensity, right? Any other sources will not come from the same direction as the sun. At night, for instance, you can do it at night, no problem. But the sun is the other side of the planet, but neutrinos will come through Earth, and again, we can point to the direction and say, it's going to the sun, coming from the sun. Okay?
Ok. ¿Alguna otra pregunta, muchachos? ¿Dudas, comentarios, críticas? Okay, Hélio.
Okay?
Okay, well,
thank you for the opportunity. It was interesting to give this presentation. Very short, very tight. Had to run a lot, but maybe people got curious about it.
Okay, well, from us, I want to thank you for this mini course you just gave us. I believe that some people who attended the lectures now is probably a little bit interested in neutrinos. I'll be happy if that's the case. So, guys, if you have any other question, please, you
I have
can.
asked in
There
in
is
the
another
comment.
one. Well,
Another question. Let's go.
another question. Go ahead, Christian.
Okay. Is there any way to measure the chirality of a particle?
Yes. To know the part with left hand or right hand.
Yeah, but the chirality, not
The helicity.
yeah, they are different, I guess, but they are the same when the particle is massless.
Yes, we can see that. Okay. Let's say the following. There are things that they are preserved, right? Momentum is preserved, the energy is preserved. And so this was done years ago. If you have a particle and you have to deal with the decay of particles, for instance. And so when you observe the decay of the particle, you can reconstruct things like the momentum, and they also have things like the angular momentum of the particle. There is a situation when the chirality and helicity coincide. Okay, when I have, I said that if you are moving a car, so the helicity of the part, that ball that I showed, you can see it as right hand or left hand. Okay, but of course, if you have a particle, you cannot go after. Take a particle that goes very, very fast, that you cannot go faster than at least conceivably. So in that case, if it's very high speed, go out of relativity, chirality and helicity will coincide. So at some point, this has to do with the angular momentum, for instance, that may cause it. So in some events, if you observe a decay of a certain particle, there was an experiment made in the 50s. Madame Vu was very famous for that. And that event, you observe the way a particle decay. And when the particle decay, it sends the particles in some directions. Okay? So you can think very well, how would be that event in a mirror? How that would change in the mirror. Remember, the mirror changes the direction of things. Okay. And then you can, but if this is true, if that thing really happens, it means that you should be able to observe both cases. Okay? Like the DNA particle. Okay? If what you see in the mirror really exists, of course, you cannot distinguish the mirror from the one, you can see both of them. So by running this experiments like that, you see if you can observe if you see the events that correspond to the left hand and the events that correspond to the right hand. Okay, what happens with neutrinos is that you observe only events that would happen with the left hand. When you do it with the left, we see events that happens with the left hand and it happens with the right hand, showing that the electron show both possibilities. But when you do with neutrinos, we see only left hand. No, so the electron has both the components. The way you see electron is that it has a component that's left hand and a component that's right hand. It has both components there. Okay? So when you run experiments and you see, okay, what the left hand component will produce, what the right hand components will produce, like putting in a mirror. And when you run the experiment, you see both happening. So you see the one from the left correspond to a left hand, and the one corresponds to the right hand. Let's make it simple. Consider just spinning. Okay, it's an angular momentum. So you see both situations happening. Okay, one right hand and the other one left hand by conservation of momentum. When you do with a neutrino, for instance, you don't see, you see only the one that corresponds to left hand. So you don't see right hand neutrinos. That's what happened. A question of conservation. And then, see, you don't do that with one event. Okay? In fact, you do it many events. You see what happens. See the distribution. And the distribution shows, well, there is nothing here that is compatible with a right hand, and nothing here that's compatible with a left hand. Yes, we have things compatible with a right hand, we have things compatible with a left hand. So both are present, not in one, but in 1,000. And neutrino, no, it's not. No matter how many times you run experiments, you don't see anything compatible statistically with the right hand neutrino. So. And also the theory, this agrees with the theory, but anyway. It's not simple.
Yeah. Okay.
Okay,
Well,
yeah.
You can show them, see them
Mhm.
later, the Madame Vu experiment. It will be interesting for them to see how things happen. Because Madame Vu
Yeah.
experiment pretty much showed that this thing is not preserved, it's not conserved, so it's not there.
so
And
Hélio,
in fact, it was a very simple experiment. What? Say it.
do you have any reference that maybe people can take a look at it later
For what? A reference for what?
for these topics?
Yes, I can send you by email a list of. When I give a course here at CBVF, I give a list of articles that the people read and then we discuss. I can send you one of them that's pretty much simple,
Okay,
and you
that would be
distribute.
nice.
You distribute.
I believe that would be nice for everyone.
Okay.
Okay, Hélio, many thanks again for your time. I believe that people enjoy your course, your mini course. I hope that
those who are not watching a YouTube video.
Yes. If everything goes well, probably next year we can meet in person.
Yes, I hope so.
Here in Lima for the next meeting of physics.
Okay. So thank you very much and see you.
See you, Hélio. Thank you. And thank you guys for these 3 days. Well, anyway, si tienen alguna otra pregunta, duda y tal, pueden mandármela por email. Dejo mi email por acá, para los que no lo tienen. @uni.edu.p o directamente a Hélio de Motta. Listo, ¿ok? Ok, muchas gracias, muchachos. Voy a estar subiendo esto los 3 días de lectures, probablemente en los siguientes días. Va a estar en el canal de YouTube y se va a anunciar también en la página del evento, ¿ok? Muchas gracias. Buenas tardes para todos. Obrigado, Hélio.